Hi, folks. So before I talk to you about what atoms are, I need to tell you what an element is. So an element is a pure substance that is made up of only one type of atom. There are 118 known elements. They're listed on your periodic table, which I'll give to you soon if I haven't yet. I've got that on the next slide. And an atom is the smallest particle of an element that still retains the properties of that element. So it still behaves the same way chemically and physically. We now know that atoms are made up of protons and neutrons and electrons, so we kind of have a vision of of an atom in our head that looks like this. But how do we know that? What kind of experiments and researchers have worked over time to give us this model of the atom? As I said, all 118 elements are listed on the periodic table, and we'll be looking more at this in the months ahead. But the first person we should talk about when we talk about atoms is Democritus. Now, he was not a scientist, he was a Greek philosopher. And so he just had an idea that he talked about. He was a philosopher, he liked to talk. He didn't have an experiment, he didn't have a proof, he didn't have evidence. But he had this idea that if you keep cutting something in half, you will eventually get a particle that is so small you can't cut it in half anymore. He gave this type of particle that you couldn't cut in half a word. He called it atomos, which is Greek for indivisible, and that's where we get our word atom from, which is why I did want to talk about Democritus. But the thing is that there were other philosophers of the time, and maybe some of them were better known than he was. I don't know, but like Aristotle is somebody that I'd heard of, and maybe not so much Democritus. And Aristotle, perhaps because he was more famous, better looking, I have no idea. But he said that all matter is continuous. You could keep on cutting matter forever and ever and ever, and you'll just get a smaller, smaller, smaller portion. You never get something that you can't cut in half. So he said there were no atoms, and his idea stuck. People kind of forgot about what Democritus said until the 1700s. So in the 1700s, at this point, most scientists agree that there are these things called elements. They are the simplest substance possible. You can't sort of break it down into a simpler substance through chemical reactions. In addition, technology has advanced to the point where people can take pretty accurate mass measurements. Before this point, people did think that matter could be created and destroyed. Just because they couldn't take careful mass measurements, they didn't realize that, hey, when there's this chemical reaction and mass seems to disappear, the mass has actually been released as gas in the air. They didn't have good ways to kind of capture gases and then measure masses in that way. And at this point, several basic laws had been discovered. So the law of conservation of mass. Mass cannot be created or destroyed. That was an accepted law. There's also the law of definite proportions. And this said that if you have a substance like carbon dioxide, it doesn't matter how large or how small your sample of carbon dioxide is, the ratio of the mass of carbon to the mass of oxygen always stays consistent. It's a constant ratio. And last, Dalton noted the law of multiple proportions, which is when you have two elements that can react to form a variety of compounds, that if you have a fixed amount of one of the elements, so for instance, let's talk about nitrogen and oxygen, since that's what Dalton actually studied. Nitrogen with oxygen comes in a few different components, or a few different combinations are possible. He noticed that whenever he held the amount of nitrogen constant and just varied the amount of oxygen and then looked at the mass ratios, that the mass ratios were always small whole numbers. So like a 1-to-1 ratio of mass versus a 1-to-2 versus using double the oxygen, 1-to-2 ratio sort of thing. And so there were these law of multiple proportions. These mass ratios are always in small whole numbers. So Dalton made the third of these discoveries, and then putting that together with the other laws that had come before him, he realized that this idea of a particle too small to be divided there was some merit to that. It was consistent with his observations. So with these careful measurements with nitrogen, oxygen gases, and being able to measure mass carefully, Dalton took Democritus's idea and converted it into a testable theory because he linked ideas of the atom to mass, and mass was measurable, and that was testable. So Dalton's idea of the atom is just a plain sphere. No smaller parts, because he didn't know there were any parts inside of an atom to talk about. And we call this the billiard ball model because it just looks like a plain sphere, like a ball on a pool table. So what were the tenets of his theory? What were his ideas about atoms? There were 5 key points. The first point is that all matter is composed of very small particles, which he called atoms. Second, he said that atoms of the same element are identical in size, in mass, and in other properties. So here we can use mass to test our ideas when we're comparing atoms. But atoms of different elements are different in size and mass and other properties. Then he said atoms of different elements combined in simple whole number ratios to form chemical compounds, like those different nitrogen-oxygen compounds that he was studying. He said in chemical reactions, atoms can be rearranged, they can be combined, they can be separated, but they don't get changed into different atoms. Once an oxygen atom, always an oxygen atom. He also said that atoms cannot be subdivided or created or destroyed. Now, you may have noticed these asterisks as we've gone around. Those asterisks are things that we now know to be false, or at least not true all of the time. And so that was with further experimentation because Dalton had a testable theory and other people came along and tested it, and many of the points of his theory held true, but some of them turned out to be false or needed a little bit of explanation. So let's look at those asterisks and see what we know about those things now. We've modified Dalton's atomic theory with further research. We now know that atoms of the same element can have different masses if the atoms have different numbers of neutrons. So for instance, there are 3 versions of carbon. There's carbon 12, carbon 13, and carbon 14. They're all carbon, they all have 6 protons in them, but they have different masses. And so not all atoms of the same element have the same mass. Most of the carbon in the universe is carbon 12, but carbon 13 and carbon 14 do exist. We now know that atoms can be broken down into subatomic particles like protons, neutrons, and electrons, and in fact those can be broken down further as well. We now know that during nuclear reactions, atoms can be created and destroyed. This doesn't happen during chemical reactions, but atoms can be created and destroyed. This doesn't totally negate the conservation of mass theory that we're creating to destroying matter, because the law of conservation of mass has a caveat that mass and energy can be interchanged. So mass can be converted to energy. Energy can be converted into mass. But that happens during nuclear reactions, not chemical reactions. So how did these modifications arise? What discoveries were made that made us realize that there was more to the atom than just a billiard ball? The next major influence on the atomic model was J.J. Thomson. And I can't play this video for you on here, but you can access the link through our notes. And he did the cathode ray experiment. Basically, he passed electric current through a low pressure gas inside of a tube, and he used kind of different metals on the plates at either end, and passed a high voltage through it, and this resulted in a glow caused by a stream of particles. And that glowing stream of particles was called a cathode ray, and in old TVs are cathode ray tube televisions. And he found that the ray was made up of charged particles, because when he brought a positive plate and a negative plate nearby, the charged particles veered towards the positive plate, veered away from the negative plate. And because of that, we know that the particles in the cathode ray must have had a negative charge. So adding those rays to your diagram, you can do that. Now, what Thomson discovered is that every different type of metal plate that he used produced these same negatively charged particles. These negatively charged particles had a tiny mass compared to the atom, so they were very small, but every single substance produced the exact same tiny, tiny particles. So he hypothesized that these particles must be coming from the atom, and therefore concluded that atoms can be subdivided after all. They're not just a solid billiard ball model. There's little particles inside here that can be separated out under the right situations. He discovered electrons. We call these electrons, and these are particles with a extremely small mass compared to the mass of an atom, but a surprisingly large charge, large negative charge for the amount of mass that they are. So he also reasoned that atoms overall have no charge. If he just found a particle with a negative charge, there must be something else in the atom with a positive charge to balance that out, because there's no way for the overall atom to be neutral, to have zero charge, unless there's something in there with a positive charge. So he's like, something with a positive charge has to be in here also, I just don't know what it is yet. So his model, his idea for what the atom looked like, he called the plum pudding model. This would have been a very popular dessert to have, a dried fruits inside, kind of like a spongy cake type of thing. Would have been very popular. It might be more realistic to have you think about it as a chocolate chip cookie. That would be a more popular dessert for you to have, perhaps, where the electrons are the dried plums in your pudding or the chocolate chips in your cookie, and then the kind of dough around the cookie has a positive charge. We know that opposites attract, so we expect the positives and negatives to be close together, but those, we only really know what's causing the negative charge. So we have the negative charges as specific chocolate chips, and the positive charge is just whatever's surrounding it. So we call this the plum pudding model, based off of the discovery of the electron. So people wanted to test this theory, or wanted to explore, okay, what does this mean now that we know about these negatively charged electrons? And so Ernest Rutherford fired a positive charge at gold foil. He didn't really know what caused the positive charge. We now know that these were alpha particles that he was directing at the gold foil. But he was expecting these alpha particles to pass straight through the foil in accordance with the plum pudding model, because these positively charged particles were very small, very dense. All the positive charge was in this very small particle. And he was firing it at this atom where the positive charge was kind of all spread out, because it's like the dough of the chocolate chip cookie. And he was just expecting these particles to be able to pass right through, kind of like throwing a bowling ball at a wall of tissue paper. You're expecting that bowling ball to just break right through the tissue paper. And again, this is because, according to Thomson's model, this positive charge should be evenly distributed throughout the atom. Now, what he found, I can't show you this video. Once again, I say please click the link from our notes. But what he found was that some particles pass through. So here was his alpha radiation source. He was shooting this alpha radiation at this gold foil. And most of the radiation did pass straight through the foil. However, some of the radiation was deflected a little bit. Its path was bent a little bit. Some of the radiation was deflected quite a lot, and a small amount of the radiation was actually reflected back towards the source. So most particles went straight, but some particle paths were bent and a few were reflected back. And he wondered why. What on earth could cause this? So he came up with a hypothesis that the positive charge wasn't evenly spread throughout the atom like a chocolate chip cookie. All of the positive charge was condensed in the nucleus in a very small region at the center of the atom. And he coined that word nucleus here at the center. And so atoms take up a lot of space because the electrons are not large, but they're just moving around in a way that takes up a lot of space. But the positive charge is all very condensed and localized at the center of the atom. Let's look at why this explains his results. If you look at this, most of the alpha particles passing through do get to go straight through the atom because they're not hitting anything at all. They're mostly hitting empty space. But some of the alpha particles, like this one, get close enough to the nucleus for the positive charge to repel the positive charge on the alpha particle and bend the path. Other alpha particles, like this one here, head straight for the nucleus, and the nucleus is also very densely charged, so densely charged that the alpha particle actually bounces back and reflects backward. So Rutherford came up with the idea of the nucleus, and because of the idea of the nucleus, it actually means most of an atom is empty space. The nucleus has a tiny volume compared to the volume of the whole atom. And so the Rutherford model looks like this, with a dense positive charge in the nucleus and the electrons kind of spread out around the nucleus. One thing that Rutherford's model does not explain is why those electrons stay outside the nucleus. We know that opposite charges attract, so why aren't those negative charges just zooming right into the nucleus to be next to the proton? So clearly more research was needed to explain why that happened, but Rutherford did observe that how the alpha particles were behaving with the gold foil, and thought that this model better represented what was happening with the atoms. Niels Bohr was a mathematician, and he used math to propose an atomic model that helped explain why those electrons stay in orbit around the nucleus. So he's explaining why the electrons aren't collapsing in to be next to the positively charged nucleus. He said that electrons move in quantized energy levels. Quantized energy level just means that you can be in energy level 1, you can be in energy level 2, but you can't kind of hang out halfway between energy level 1 and energy level 2. An electron is either in energy level 1 or energy level 2. It can't be in between the two. While this may sound a little far-fetched and hard to understand, you can think of it kind of like a staircase. You can stand on the first step of a staircase, you can stand on the second step of a staircase, you cannot hover in between step 1 and step 2. With this idea of energy levels, he said that electrons have predictable orbits around the nucleus with fixed size and energy. So kind of like the Earth and Mars and Mercury have their orbits around the sun, where the planets are moving fast enough to not collapse into the sun. Similarly, these electrons are moving fast enough at their various energy levels to not collapse into the nucleus. Unfortunately, Bohr's model only worked for atoms with one electron. His calculations, his equations worked absolutely perfectly for hydrogen, but not for other elements. So clearly his model was good in the sense that it worked for hydrogen, but flawed in that it didn't work for anything else. So clearly more research needed to be done. Notice that this version of the Bohr model looks a little different to the previous one. Here, the nucleus is we know the nucleus is positively charged, but we don't know why. But then subsequently, we did discover protons, which have the positive charge, and neutrons, which are also in the nucleus. And so we do sometimes modify the planetary model with protons and neutrons, even those were discovered later, so kind of like an updated planetary model. But we call this the planetary model, or the Bohr model, because it does look like planets orbiting around the sun. Even though we now know that this isn't really how electrons move around the nucleus, we still use this model a lot because it's easy to interpret, looking at this, I can easily see that this atom has 6 electrons, and pictures of the more modern uh, model of the atom, the quantum mechanical model, are more difficult to read. So this is actually easier to read, even though it's perhaps a less accurate representation of what we now know atoms are. So we did discover protons and neutrons. Those are separate experiments with actually a lot of people involved. Some people say Rutherford discovered the proton. Other people were involved. It certainly wasn't Rutherford all on his own. But we discovered protons and their mass. So then we knew that the nucleus wasn't just one big positive charge. It was made up of several particles, each with a positive charge of 1. And we knew their mass. But once we knew their mass, and once we knew how many protons were in the nucleus, we discovered that adding up the mass of protons and the mass of electrons did not account for the mass of the entire atom. So something was missing from this model. We knew there was something else in the atom. We didn't know what it was. It took quite a bit of time to discover the neutron, that missing particle, because neutrons have no charge. So they were a little harder to detect. And so it took a while to discover neutrons and their mass. But then once we knew about protons, once we knew about neutrons, we can kind of have this improved planetary model. So I've already alluded to the fact that we know that electrons don't move in fixed orbits around the nucleus. Schrödinger came up with a wave equation to explain the kind of wave particle properties of electrons. Electrons don't just behave as a particle, they also behave as a wave. And Schrödinger's equation did explain how energy levels could work, this idea of quantized energy levels, even when an atom has more than one electron. So his model didn't just work for hydrogen, it works for all atoms. So it was better than Bohr's model in that sense. He, together with Heisenberg, did disprove Bohr's idea that electrons have nice, neat, fixed orbits, because we found that you couldn't know the speed and position of a electron. You can't know both things at the same time. Instead, electrons exist in orbitals, which are sublevels of an energy level. So he took Bohr's idea of energy levels and broke it into parts, which we call sublevels. And it's just a likelihood of where you might find an electron. We can't know where for sure, but it's a probability zone of where we're likely to find an electron. You do not need to know Schrödinger's wave equation, but you do need to know that orbitals are three-dimensional regions in space around the nucleus where there's a high probability of finding an electron. Sometimes orbitals are spheres, sometimes they're this kind of dumbbell shape. They can be much more complicated than that, but those are the simplest two shapes for orbitals. And as I said, Heisenberg came up with the uncertainty principle, which said it's impossible to know the velocity and the position of an electron at the same time. So this is the best we can do. Say, hey, there's a 90% chance of finding an electron in this zone. If this is representing, so these are both images that are trying to represent the quantum mechanical model. As you can see, it's kind of hard to represent. There's a 90% chance of finding an electron here. Because if this is representing a hydrogen atom, hydrogen only has one electron, but the way I've drawn this picture makes it look like hydrogen has 1,000 electrons. But here I'm just trying to show you where there's a high probability of finding that electron. And then this picture, I'm not even drawing electrons at all. I'm just showing you the regions where the electron might be. So you can see where Bohr's model, even though aspects of it are inaccurate, is useful because it actually shows you how many electrons. It's easy to read in terms of how many electrons an atom has. But these are different ways to depict the quantum mechanical model. I hope this helped.